Hello everyone, welcome to our lecture video. In this lecture video, we are going to calculate the slope and deflection of this simply supported beam by using double integration method, and we are going to explain the basics related to double integration method as well. We have already created lecture videos regarding how we can calculate the slope and deflection of any beam by using other methods such as Macaulay methods, Macaulay method, conjugate beam method, and moment area method, whose link you can find in the description box below. So right now we're going to talk about double integration method. So unlike other method, we can use double integration method only when our flexural rigidity EI, which is known as our flexural rigidity, when it is constant. In that case only we can use our double integration method. In the case where our EI is not constant, in such case we can use our other methods. So first of all, we are going to use our simple formula EI d square y divided by dx square equals to mx. This is our differential equation for deflection. So we're not going to talk much about this. We're going to talk about how we're going to use this formula. So we have EI d square y divided by dx square equals to mx. And now regarding for our mx means our moment of all the reactions and all the forces involved in this equation. So double integration method will be more clear when we'll be solving this example. So let's move on to our example. So here we have a simply supported beam with the three forces of 1 kN, 2 kN and 3 kN acting over here. So let me just write down the point name A, B and C, D and E. So we have our first reaction RA, then we have our second reaction RB. So we need to firstly find out the value of RA and RB respectively. So in order to find those forces, firstly what we are going to do is we are going to take our upward forces as positive. So what we are going to do is we are going to use the sign convention plus EFY equals to 0. We can take your downward force as positive as well, it's up to you. So next we have RA plus RB equals to 1 plus 2 plus 3, 1 plus 2 plus 3. Since they are acting downward, they are going to be taken as positive. So we get our first equation, RA plus RB equals to 3 plus 2 is 5, 6 kilonewton. Next we are going to take moment about A at 0, or else we can take your moment about B at 0 as well. So first we are going to take our moment about A equals to 0, and we will be taking our clockwise moment as positive. We can take your anti-clockwise moment as positive as well. So firstly we have our 1 kilonewton is acting at a distance of 1 meter, and with respect to A, as you can see here, it is going to produce clockwise moment. It is pushing downward, so it's going to be producing clockwise moment, and since we are taking clockwise moment as a positive, so it's going to be positive. So we have 1 into 1 plus 2 into 2 into the distance of 2 kilonewton from A is 1 plus 1 2, and likewise 1, it is producing the same clockwise moment, plus 3 into 3 equals to RB into, so right now I'm writing RB in the right side because RB is going to produce anti-clockwise moment with respect to A. So as you can see, with respect to A, RB is pushing upward, producing anti-clockwise moment, and anti-clockwise moment are taken as negative. RB into 4. On solving this, we are going to get our value of RB as 3.5 kilonewton. And so from, if we substitute the value of RB over here, we're going to get the value of RA as 2.5 kilonewton. So firstly, after calculating our reaction forces, we are going to use this equation. Equation in order to calculate our slope and deflection. So our first and foremost step is computation of reaction forces. So we have successfully calculate our two reactions RA and RB. So next what we're going to do is, so let me rewrite the formula of double integration method one more time. So our formula for double integration method which we're going to use is EI d square y divided by dx square equals to mx. So I've already explained before, our EI is flexural rigidity, which is going to be constant. D square y divided dx square is our second order differentiation. Next we have mx. As I explained before, mx is simply moment about section x. So we're going to take a certain section x in this figure. So where are we going to take our section x? We're going to take section x in a such a way that it incorporates maximum amount of forces. So I have my end A over here and I have my end B over here. So if I were to take a section x from my end A, it is going to be at this point away from 3 kilonewton over here. over here. This way I will include all the forces. I'll include RA 1 kilonewton, 2 kilonewton and 3 kilonewton, while if I was taking the section X from B, I will take it over here. In this way I will include RB 3 kilonewton, 2 kilonewton and 1 kilonewton respectively. So right now I'm going to take my section at a distance X, from X from end A. So it is going to be at a distance X from end A. And as I explained before, right now I am taking clockwise movement as positive. So let me firstly write down my mx. So mx is going to be, so right now RA is at a distance of X, and with respect to this point RA is producing clockwise movement. It is rotating, it is trying to rotate in clockwise direction, so it's going to be positive. So our value of RA is 2.5 into X. So let me just draw a line to represent my first force is completed. So next I have 1 kilonewton. So with respect to this section, which is at a distance X from A, 1 kilonewton is going to produce anti-clockwise movement, which is acting downward. 2 kilonewton is also acting downward, so anti-clockwise. 3 kilonewton is acting downward, so anti-clockwise. So all are going to be negative. So let me write down minus 1 into, now for the distance, if A is acting at a distance of X, 1 is going to be acting at a distance of X minus 1. So as you can see over here, so this much distance from this section is going to be simply X minus 1. And so let me write down 1 into X minus 1. Let me draw the line again. So again minus 2 into, so this is going to be at a distance of X minus 2. Minus 2 into X minus 2. So let me draw that line over here. Draw one more line. Minus 2 into X minus 2 minus 3 into, so 3 is going to add a distance of X minus 3. 3 into X minus 3. So our mx, which is our moment about section X, has been completed. So this is my mx. Next what we're going to do is I'm going to write this down. So I have EI d square y divided by dx square equals to mx, and now I'm going to write down my value of mx, which is going to be 2.5 into x. Draw this arrow line to mark the beginning of new force, minus 1 into x minus 1 minus 2 into so I can drop this down, minus 2 into x minus 2, next line minus 3 into x minus 3. So I'm going to mark this as my equation first. So what I'm going to do first is, so with the name double integration method, so what we're going to firstly do is, in order to calculate our slope and deflection, we're going to integrate this equation. So firstly we're going to integrate equation 1. So let me write down here integrating equation first. So integrating equation first, we're going to get EI. So if we integrate d square y by so if I'm going to integrate d square y by dx square dot EI, so since EI is a constant, is going to come out, and d square y by dx square, so this is dx square, so this is going to be my this is going to change into EI dy divided by dx. Since I'm integrating with respect to x, the second order changes to first order under integration. So this is a simple mathematical rule. So I have EI dy divided by dx equals to 2.5 into x becomes x square by 2. So right now as you see, so let me just show one simple step of integration. If I integrate x, I'm going to get x square by 2, and there's going to be a constant as well. There's going to be a constant plus c whenever I am integrating. So I'm going to get one more one constant over here as well. So I'm going to write a constant as plus c1. The constant is going to be at the first, not at the end while integrating, so you need to remember that. So whenever you are writing the constant, you need to write as soon as you finish the first term, not at the last. So let me draw my line as well. Minus 1 into, so x minus 1. So normally when I am integrating x minus 1 under the integration x minus 1, so x dx will be x. So right now I am integrating with respect to dx. So right now if I am integrating x minus 1 dx, so what I am going to get normally in integration is x square by 2 minus x plus x square minus 2 minus x square by 2 minus x plus some constant. But right now we're following a little bit different method of integration. So under this method we're going to treat x minus 1 as x only. X minus 1 is going to be treated as x only. So x minus 1 under integration over here is going to be x minus 1 whole square divided by 2. So fully you have understood what I have explained over here. So let me explain this one more time. So our under normal method of integration, x minus 1 dx is going to be x square by 2 minus x. So that is our normal integration, but in our double integration method we are going to calculate x minus 1 in a little bit different way. So we are going to treat x minus 1 as x. So whenever we're integrating x, we're going to get x square by 2. So whenever we're integrating x minus 1 in double integration method, we're going to get x square by 2 only, but instead of x we have x minus 1, so it's going to be x minus 1 whole square by 2. So fully have understood this, so let me just write down x minus 1 whole square by 2. So let me draw my next line. So we're not going to write down another constant because we have already written constant c1 for the whole equation, minus 2 into, so x minus 2, again we're going to treat x minus 2 as x only, so it's going to be x minus 2 whole square divided by 2 dot dot minus 3 into x minus 3 whole square by 2. So it's going to be my second equation. So fully have understood till over it. So if you have any queries, we can comment down below. I will answer you there personally. So as you can see over here, from our equation, on integrating our equation 1, we have got this equation, we have got this equation 2. So in our equation 2, what you can see, we have found out dy by dx. So what does dy divided by dx refer to? So our dy by dx refers to our slope. It refers to our slope. So if we need to calculate a slope of this slope of this beam, we are going to use our equation 2. You can note down till over here. So it's going to, this equation 2 is going to be very important. So next what we are going to do is we are going to integrate one more time our equation second. So as you can see here, we did our first integration over it, and now we have done our second integration over here. So we get ey on integration dy by dx over y. So it's going to be like this, dy by dx dot dx. So it's going to be y. So it's going to be y ei equals to, so as you can see over here, firstly we complete our first integration. Now we're doing our second integration. Since we are going to integrate 2 times in this equation, this method is called as double integration method. So now we'll complete our integration. So ei dy equals to 2.5 into x square. So as you can as you know, x square dx equals to x cube by 3, but we have in denominator 2, so it's going to be into 2, so we're going to get x cube by 6. So we're going to get our x cube by 6. So this is going to be 2.5 into x cube by 6 plus whenever we are integrating a constant, we are going to get c1x. So we're going to get a c1x over here plus c1x. Since we are integrating second time, we're going to get one more constant plus c2. So let me draw this line, minus 1 into, so right now we are going to treat x minus 1 again as x. So it is going to be x minus 1 cube divided by 6, same as over here. 3 comes from integration, and 3 into 2 is 6 minus 2. So while integrating this, you might get confused, but what you need to simply understand is we are going to treat all this x minus 1, x minus 2 all as constant x. So we're not going to so we're simply integrating x square, and while writing down, we're just going to write down whatever it is here. X minus 1 gets written as x minus 1, x minus 2 gets written down as x minus 2. So integrating this, we're going to get x minus 2 cube divided by 6. Again draw this line, so let me write down over here, minus 3 into x minus 3 cube divided by 6. So it's going to be my equation 3. So as I explained before, we're going to use equation 2 for our slope, while we're going to use our equation 3 in order to calculate our deflection. Here our y represents our deflection. So in this way, we have found out our important equations, equation 1 and 2. So we are going to use some boundary conditions in order to find out our value of c1 and c2. So here our c1 and c2 are unknown from both of these equations. So we're going to use certain our certain boundary conditions. So I'll be explaining what is boundary condition a little bit later on. So firstly, you can note down our equation 2 and 3. I'm going to rough down every portion. So now I have written down my equation second and equation third. So as I explained before, we have our two unknowns. Our unknown are c1 and c2. So firstly, we need to find the value of both of these equation, c1 and c2, in order to calculate our slope and deflection of the different section of our beam. So as I explained before, now we're going to apply our boundary conditions. So what are our boundary conditions? So what does our boundary condition refer to? So right now we're going to use our equation 3. So let's focus on equation 3. So in our left hand side we have our y, which is our deflection. So as you know, for a simply supported beam, so if I were to draw the deflection of this beam, so it will be something like this: a, b, it's going to be like this. The deflection is going to be 0 at our boundaries, which is at point A and point B. So whenever our deflection is going to be 0, we're going to use those conditions. So when is our going to get when is our deflection going to be 0? So as you can see here, in our right term we have x. So our equation is basically expressed in terms of x. So our x was a certain section, so we can move that section left or right. So as you can see here, when x equals to 0, 0, we are at A. So right now we are not taking any section, so our section was like this: x. This is our section x. So when x equals to 0, it is going to be at point A. So our deflection, which is our y, is going to be 0. Similarly, when x equals to 4 meter, which means we're at point B. So x equals to 4 means so this section x reached over here at B point. Again, our deflection is going to be 0. So we're going to use these conditions to find out our value of C1 and C2. So as explained before, for our integration we treated x minus 1, x minus 2 as x. So there's going to be a little bit different rules for our for regulating this as well. So let me just move on directly. So ey0, it's going to be 0. So 2.5 into x means 0 cubed by 6, it's going to be again 0, plus c1 into x, x is 0, so it's going to be 0, plus c2. So when we are moving this side, so whenever I am putting 0 over 0 in this equation, I get, so let me just write down this equation over here. So minus 1 x minus 1 cube divided by 6. This is going to be, whenever I am going to put 0, I'm going to get 0 minus 1, so I'm going to get just negative. So whenever I'm getting my inside term as a negative, I'm going to ignore this term. Similarly for this term, 0 minus 2, ignore it. 0 minus 3, simply ignore the term. We're not going to include all those terms. This is our second rule. So our first rule was treating x minus 1, x minus 2 as a x. So our second rule is going to be, whenever we are going to get 0, whenever our term is, whenever our x is going to be greater, whenever our x is going to be less, in that case we are going to ignore all those terms. So from this we are going to get our value of C2 as 0. So let's move on to this term. So let me explain this rule a little bit clear over here. So when x equals to 4, y equals 0, when our left is going to be 0, equals to, so we have 2.5 into x is 4, 2.5 into our x is 4 cube divided by 6, plus our C2 is already 0, so plus C1 into 4, C1 into 4, let me just draw our line, minus 1 into x minus 1, so it's going to be 4 minus 1 cube divided by 6. So as you can see here, in this case our x is greater, so we're not going to get our negative, so 4 minus 1 is 3, but previously when we were getting 0 minus 1 is going to be negative, so we had to ignore this term. So if we're not a little bit clearer for this, this will be more clearer when we will be calculating our slope and deflection. So do watch the video till then. Minus 2 into 4 minus 2, so this is again positive, so we're going to include this. Minus 3 into 4 minus 3, again positive, 4 minus 3 cube divided by 6. On solving this, we are going to get a value of C1, so which is going to be equal to minus 4.75. So we have found out our value for C1 and C2. So let me just drop this. So fully we have understood our boundary conditions and how we used it to calculate our value of C1 and C2. So we can write our equations. So as you can see over here, our C2 is 0, so we can simply drop this, and our C1 is minus 4.75, so it's going to be minus 4.75, so let me write down minus 4.75 x. So our this C1 is also going to be 4.75. So as I explained before, we are going to use this equation in order to calculate our slope, while we are going to use this equation to calculate our deflection. So let's firstly use this is going to be our slope equation. This is our slope equation, while this is my deflection. Deflection equation. So as you can see over here, this is my slope equation, and this is going to be my deflection equation. So if I have to calculate my slope at any point on this on this simply supported beam, I'm going to use equation number 2, while for deflection I'm going to use equation number 3. So let's calculate our slope and deflection. So first let me calculate my slope equation. So first let me just, so this is my slope equation. So let's say if I have to calculate my slope, so at x equals to 0, which means at point A my slope, which is going to be theta A, is going to be equal to 2.5 into 0 square by 2, 2.5 into 0 square by 2. So this is actually negative, so we had found out our value of C2 to be minus 4.75, so this is negative minus 4.75. So as I said, you'll be much more clearer when I'll be moving on over here. So as I said, if I put my value of x over here, I'm going to get 0 minus 1, which is going to be minus 0 minus 1 negative. So we're going to ignore that term. We're not going to think about the square. So 0 minus 1, which is minus 1, whole square will be 1. But no, we're not going to think about that term. We're going to simply see whether the term, if you just, we're going to see this term x minus 1. If I put 0 over here, I'm going to get 0 minus 1, which is going to be minus 1 negative. So ignore those terms. Again, x minus 2, I'm going to get 0 minus 2 minus 2, ignore that term, which means we're going to simply ignore all the terms remaining behind. So what does this mean in real is, whenever I'm taking x equals to 0, I'm just incorporating the force which is at x equals to 0 meter on which is at before this point 1 kilonewton. So x minus 1 refers to our 1 kilonewton. So this force is not going to include it. All these forces are not going to be included, so they all need to be neglected. So right now my section is over here. The forces before it are 2.5 into x square by 2 and minus 4.75 only. So this is what my section refers to. That's why I have told you from before to draw this section. So in order to understand it is simply not to go as positive or negative. What you can think is, so at x equals to 0, I'm going to take these terms. At x equals to 1, I'm going to take up to here. At x equals to 2, I'm going to take up to this section, so up to this bar. While at x equals to 3, I'm going to take all the terms. So hopefully you have understood why we are why we are excluding those terms. So I'm going to get my value of theta a as so in my so I have EI in my left hand term, so we need to include that as well. So I'm going to get a value of EI as minus 4.75 divided by A. So my slope at A, theta A, is going to be minus 4.75 divided by EI. So next I'm going to calculate my slope at x equals to 1 meter. At x equals to 1 meter, which means I have reached my point C, theta C. Theta C is going to be, so let me just write down 2.5 into 1 square by 2 minus 4.75. So as I explained before, at x equals to 1, I need to move up to this section, so it's going to be minus 1 into x minus 1 is my 1 minus 1 whole square by 2 divided by EI of left hand side. So I'm going to get my value of theta C as theta C is simply going to be minus 3.5 divided by EI. So hopefully you have been understanding up to here how I'm calculating my slope. So let me just move up to here so I'm going to calculate at x equals to 2 meter, at x equals to 3 meter, and at x equals to 4 meter. So I need to move up to at x equals to 4 meter. So at x equals to 2 meter, I'm going to get my value of theta d, and at x equals to 3 meter, I'm going to value of theta e, and x equals to 4 meter, I'm going to get value of my theta b. So let me do one more term over here at theta d. So at x equals to 2 meter, I'm going to get so this is going to be 2.5 into 2 square divided by 2 minus 4.75 minus 2 minus 1 is 1 square by 2 minus 2 into 2 minus 2 is 0 by 2. So we're not going to include this term. So at x equals to 2, we're going to move up to here, and so in this way we're going to get certain value for this, and my at x equals to 2 meter, I'm going to get my slope as minus 0.25 divided by EI. So I'm not going to explain all these terms, so we're just going to simply put down your value of x, and you're going to get your required slope. So if you have found out the answer for 3 meter and 4 meter, do comment down below. I'll be telling you whether you have found the correct answer or not. So next we're going to calculate our deflection. So let me just stop this. So do comment down below what you have found out the slope at E and B. So now we are going to go for our deflection equation. So this is our deflection equation. So ei, this ei 2.5x cubed by 6, all this long question, this equation number 3 is our deflection equation, and we are going to use this to in order to calculate our deflection. So it is quite easy. So we're going to do the same when x equals to 0 meter, where we have reached point A. So deflection at A, so which is going to be ya. So as I have already explained before in my boundary condition, my deflection at A and B of at the supports is all going to be 0. So you can just put in the value like 2.5 into 0 cubed by 6 minus 4.75 into 0, while all the remaining terms are going to be neglected, so simply going to be 0. So what you can do, your simple trick is when x equals to 1, yc equals to something, when x equals to 2, when, so I must write down over here, when x equals to 4 meter, I'm going to reach yb, and again multiplication is going to be 0. So you can just use this simple trick. So add the ya and yb, it's always going to be 0, so you don't need to calculate. So when x equals to 4 meter, you get your yb as 0. Your deflection at the ends are always going to be 0, so you can just simply do this. Otherwise you can put 4 over, you're anyways going to get 0. So next we're going to get our deflections at C, D and E. So when x equals to 1 meter, so just we can, so this is not, so hopefully you have understood for 4 meters as well. So let me now do firstly for 1 meter. When x equals to 1, we reach at yc. So what we're going to do is we're going to put our value of 1 instead of x. So 2.5 into 1 cube divided by 6. So it's just a simple part. If you have understood how we have calculated our slope at different points, it's just the same, but we are using equation 3 this time. So when yc will be equal to 2.5 into 1 cube by 6 minus 4.75 into 1. So when x equals to 1 meter, we are going to move up to here, all the terms are going to be ignored, minus 1 into 1 minus 1 is 0 cube divided by 6. So as you can see, 1 minus 2 minus 1, so these terms are going to be ignored. So we are going to divide by ei. So we are going to get our value this as minus 4.33 divided by ei. Similarly, when x equals to 2 meter, we reach yd, and when x equals to 3 meter, we reach ye. So yd is going to be 2.5 into 2 cube divided by 6 minus 4.75 into 2 minus 1 into 2 minus 1 is 1 cube by 6 minus 2 into 2 minus 2 is 0 cube divided by 6 divided by ei, and we're going to get this value as minus 6.333 divided by ei. Similarly, when x equals to 3 meter, so we're going to move up to here only. So we're going to get 2.5 into 3 cube divided by 6 minus 4.75 into 3 minus 1 into 3 minus 1 is 2 cube by 6. So just look at this equation and put down your values. Minus 2 into 3 minus 2 is 1 cube by 6. This is going to 3 minus this is going to be minus 0 divided by ei, whole divided by ei, and we are going to get a certain value of this. So do the calculations on your own, and you get your value this as minus 4.667. So if you have any queries, you can comment down below, and for the slope, do comment down the answers below how much you have find out. I will answer you whether you have found the right solution or not. And if you have any queries, you can comment down below, and if you like our content, do subscribe and do like the video and share with your friends to support us. Thank you.